Thank you. All right. No worries. Always good. Okay, so I'll mute myself as soon as we start. If there's questions, ask on YouTube, or I'll ask here. Okay. So it's a pleasure to introduce my kid Lawrence. No, it's a pleasure to introduce Matthew Leifer, who's joining us from Chapman, where it's now a bit past midnight in California. So we're doubly happy that he's here with us. He's like the only returning. He's the only returning lecturer of the summer school. We like him so much that every year we invite him to give a lecture on a different topic, and one day we'll write a book just with his lectures. So without further ado, Matt, the room is yours. I will have to leave briefly for a few minutes. Let's see in a second.
Okay, I hope everybody can hear me. Yeah, I'd like to thank you, Lydia, and it's true that apparently I am the only person who's lectured at all 3 Solstice of Foundations summer schools. Lydia said it's because my lectures are so good, but I think it might be because they were so bad that they keep on wanting to give me another chance to finally do it right. So what I'm going to talk about today is epistricted classical theories as foils for quantum theory. But let's start by talking about this word foil as it appears here. Let me see, how do I change? Oh, there we go. Okay, so the idea of foils for quantum theory, we were starting to talk about these kinds of things in the early 2000s, and then there was a book published several years ago about this topic. If you go to Google, I found this quite amusing. If you go to Google and type in the definition, ask for the definition of foil, it says it is a person or thing that contrasts with and so emphasizes and enhances the qualities of another. And I like this example sentence. It was, the earthy taste of grilled vegetables is a perfect foil for the tart bite of creamy goat's cheese. So what are we doing with foil theories? So foil theories are theories that aren't quantum theory. In fact, they are theories which are unlikely to be true theories of nature. They're not designed to be true theories of nature, so they're not, they're just fictions. But they're designed to highlight or to try and explain some of the features of quantum theory. That's the point of them. So what we want to do is we want to be able to answer questions like, what's responsible for the information processing advantages that are offered by quantum theory over classical theory? And we want to ask questions like, which features of quantum theory can be regarded as genuinely non-classical, whatever that word means. Now, if you just have quantum theory and classical mechanics on their own, it's really difficult to answer those kinds of questions because, you can just say that everything about quantum mechanics, every feature of quantum mechanics follows from just the Hilbert space axioms, right? So you have Hilbert space quantum mechanics, it has everything, right? So that doesn't really help you to answer the questions. But if you get a bit of altitude and you start constructing other theories or other ways the world might possibly be, you can start to see what's really the logical connections between different features, right? Is it necessarily the case, for example, that in every theory where measurements disturb the state of the system, you'll get something like quantum interference occurring, for instance? You can ask those kinds of questions if you have theories other than quantum and classical theories. Now, there have been 2 main ways of doing this. One way, which you're going to be hearing a lot about from John Selby, is operational frameworks. The idea there is that you just take the idea that a physical theory is supposed to produce predictions for experiments, probabilities for experiments as the fundamental idea. You don't worry about any underlying reality, and you ask yourself, what does the most general such theory look like? Okay, so that's the idea there. But we can also have ontological foil theories. So these are theories where from the very start, you have a concrete notion of what reality is like, what what things exist and how they behave. And this is sort of, these kinds of theories are designed to show that, you know, when we talk about quantum theory, we often say, well, this can't be explained in terms of any sort of reality or anything like that. But you're trying to investigate the sorts of reality that that you can have consistent with the phenomena of quantum theory. Okay, so however, this question, what's genuinely non-classical, is again rather fraught for two reasons. So there's two things we have to bear in mind when we're doing this. One is what you mean by genuinely non-classical obviously depends on the number of assumptions you make about your classical models. So depending on that, you can either make every single thing you can think of genuinely quantum, so genuinely non-classical, or you can make nothing genuinely non-classical. So let me explain the two extremes, right? So if your definition of classical is classical mechanics, classical electromagnetism, and the atomic and the Rutherford model of the atom with the nucleus and the electron going around it, then we know that classical mechanics predicts that the electron will radiate and go in, and matter won't be stable, right? So everything will disappear into radiation, right? So the very fact that anything is here at all, the very fact that there are any objects, you can say is genuinely, as a quantum phenomena, right, is genuinely non-classical. If you make that strong assumptions about what classicality means. On the other hand, at the other end of the spectrum, you could just say, all I mean by classical is a model that uses classical probability in some way, okay? And you have interpretations of quantum mechanics which only make use of classical probabilities, such as, for example, de Broglie-Bohm theory. In there, it's just ordinary classical probabilities that you have. And then you could say, okay, well, 100% of phenomena are classical in that sense, okay? So you have to be sort of very clear what you mean. I would rather that we got rid of these terms like genuinely non-classical, and we have to be sort of very specific about the kinds of assumptions that we want to make. There's another thing which often happens, which is it also depends on what you call the phenomenon, right? So this is easy to illustrate by an example. So, for example, you might ask the question, does this state, the singlet state, have a local hidden variable model, right? Well, it depends on what you do with it, right? If I only measure the two systems in the same basis, then I get the kind of correlations that I have in the EPR paradox. And in the EPR paradox, yes, that can be modeled by a local hidden variable model. In fact, that's exactly what Einstein was suggesting we ought to do. Okay, so if I say I only measure in the same basis, then yes, there's a local hidden variable model. But if I now say, well, you can measure in any basis you like, you know, the two wings of the experiment can be measured in different bases, then I can get the kind of correlations that we have in Bell's theorem, and then no, there's no local hidden variable model, right? So Bell correlations are non-classical in that sense. But if someone came along and claimed that the EPR paradox, so if someone claims that the EPR paradox has a classical explanation, and then if you were to say that it doesn't because of Bell correlations, then that would be an incorrect argument. It's shifting the goalposts, right? So not only do we have to be very clear on what we mean by a classical model, we have to be very clear on which aspects of the phenomenon we're talking about that we're interested in modeling. Okay, and so you'll often in the literature have arguments going backwards and forwards about whether some phenomenon is classical or quantum, and they're just based on sort of different notions of what the phenomena is and different notions of what classicality is. There is no one single notion. Okay, so the theory that we're going to be looking at mostly for these lectures is called the Speckens toy theory. It is, to my mind, the most interesting ontological foil theory so far. You know, the challenge to come up with something even more interesting is there. It reproduces many features and phenomena of quantum theory that are usually thought of as puzzling. And one of the interesting things about it, and this isn't often emphasized in introductory treatments, is that the theory, the ontological theory that underlies this literally is classical mechanics. It's just the Hamiltonian formalism of classical mechanics. And the only thing that's different from the usual way we talk about classical mechanics is that we impose a restriction on how much can be known. So it's a bit like you take classical mechanics and you impose something like the uncertainty principle on top of it. You restrict what can be known, but still it's just classical mechanics underlying that. In particular, it's going to be a local theory, it's non-contextual, and it is psi-epistemic. In fact, when it was first introduced by Rob Speckens, it was designed as a model to defend the psi-epistemic point of view. And I'll explain what that is briefly in a minute. So I used to tell everybody that they needed to read the original toy theory paper, but actually in 2021, two of the organizers, as well as somebody else, produced a review article about this stuff with a very contemporary point of view. This is a very good article to get a first feel of the subject. So I now recommend looking at that one. All right, so let's move on. Oh yeah, so I just want to explain this psi-epistemic versus psi-ontic terminology. So the psi-epistemic point of view is the position that quantum states are states of knowledge, as opposed to states of reality. So the position that quantum states are states of reality or physical states is called the psi-ontic view. So by an epistemic state, really all I really mean is that it has the same kind of status as a probability distribution does in classically, okay? So think of it as some kind of analog of a probability distribution. When you flip a coin and it lands either heads or tails, the probability distribution is 50-50, but the coin is always either heads or tails. It's never like in an indeterminate situation. The 50-50 just represents your knowledge, the fact that you haven't seen the outcome yet. Okay, so that's the idea. The psi-epistemic point of view has a lot of virtues, and one of the points of the Speckens toy theory was to point that out. So we like to call the psi-ontic view, or if you take the psi-ontic view, then you are a psi-ontologist. So as you can maybe tell from this, I prefer the psi-epistemic point of view. Okay, but let's move on. So the outline of the two lectures I'm going to give today and tomorrow, we're going to talk about the simplest version of the toy theory in the way it's traditionally been presented. We're going to do a few explanations of quantum phenomena in the theory. We're going to spend quite some time talking about quantum interference and how it works in this theory. That's the subject of a recent paper that I wrote with some co-authors, which we'll talk about then. Hopefully tomorrow, I'll get to talk about this notion of quasi-quantization, which isn't often talked about in introductory treatments, but it's very important. It's how you can see that this really is a version of classical mechanics. Okay, so those are the main topics that I want to cover. So I'll start with the toy bit theory. It's the simplest one. Okay, so first of all, I want to probably review for most of you, the relationship between bits and questions, right? So if you have a system that can be in n possible states, then it takes the logarithm to base 2 of n bits to specify that state. But here's the way that I want you to think about this. So the question is, what is the minimum number of yes/no questions you have to ask in order to specify the exact state? Okay, so in order to get the minimum number of yes/no questions as opposed to just some set of yes/no questions, you want each question to cut the set of possible states in half. Okay, there's more than one possible set of questions, but the minimal number is unique and equal to the number of bits, right? So let's look at an example of that, right? So here's an example of a minimal set of questions. So if I have a system that can be in 4 states. Okay, that's these 4 bit strings. I can ask 2 questions. I can say, is the first bit 0? And then if it is, or if it isn't, then I narrow down in either case to only 2 possibilities, right? So I've halved the number of possibilities. And then I can ask, is the second bit 0? And once I've done that, I have narrowed it down to just 1 choice each, 1 possible choice each. Okay, so it takes 2 questions. That's a minimal set. It's not the only minimal set, though. I could ask other things. I can say, are there an even number of zeros? Okay, so either 2 zeros or 0 zeros. And here we have an odd number of zeros. Okay, so I've still cut in half the number of possibilities, and then I can ask again, is the first bit 0? And that's another minimal set of questions. But any such minimal set will have 2 questions in it in this case. Okay. So the reason why I wanted to go over that is because the way that toy theory works is by imposing what's called an epistemic restriction. So this is a restriction on how much you can know about a physical system. So in the original toy theory paper, this was done by imposing what is called the knowledge balance principle. Okay, so that works like this. So you have some system which can have n states, say. Look at a minimal set of questions required to determine the state of the system exactly. And that restriction is that at most you can know the answer to half of them. Okay, and you're completely uncertain about the answer to the other half. Okay, so for example, and this is the simplest non-trivial case, if we look at a system that has 4 possible states, as we were just looking at, we know it takes 2 questions to specify the state. That's the number of bits required to specify the state. So we can know the answer. The epistemic restriction says you can know the answer to one of those questions and not the other one. Okay. So this system contains 2 bits of information, but I should have said I meant to say qubit here. It's going to be the analog of a qubit. So a system with 4 possible states that satisfies the epistemic restriction, the knowledge balance principle, we're going to call a toy bit. Okay, so let's get a bit more concrete. So the physical state of a system, so what really exists in reality, independent of us, is called its ontic state. For a toy bit, there's going to be 4 possible ontic states, and we'll just label them by the 4 possible bit strings. And if you like, you can imagine that the physical system that we're talking about is a ball that can be in one of 4 boxes, and the boxes are laid out in a grid like this, right? So the first bit tells you whether you're at the front or the back, top or bottom, and the second bit tells you whether you're on the left or the right. That's just an example, but these are just abstract states. Now, an epistemic state is going to be a probability distribution. So the probability distribution we can write out as a vector. We need to specify the probability of each of the 4 ontic states. Okay, so it'll be a 4-component vector, just a set of numbers set of 4 numbers that sum to 1. But not all possible probability vectors are compatible with the knowledge balance principle. Okay, so for example, consider the question set, is the first bit 0? Oh, sorry, they should have said 0 here as well. I need to correct that. So consider the first question set that we had back here. Let me go back and this question set. So is the first bit 0 and then is the second bit 0? That's the question set we're considering. Suppose we know the answer to the first question, but not the second. Then we can't know anything about the second. Okay, so we can know whether the first bit's 0 or 1, but then we must be completely uncertain about the second bit. So that means if the first bit's 0, we would have this probability distribution, and if the first bit's 1, we would have this probability distribution. So those are the probability distributions compatible with the knowledge balance principle in that case. Excuse me. So there are actually 6 epistemic states, 6 probability distributions that are compatible with the knowledge balance principle, and here they are. So a few different notations here I'm going between. So so a couple of slides back, I showed you the ontic states laid out in a grid, and I can denote a probability distribution over these states by just coloring in the squares that have non-zero equal probability. So in this case here, this means that these two ontic states have probability 1/2 each, and the white ones have probability 0. I'm also using this notation with the this sort of fake Dirac notation with a curved bracket to sort of indicate that in the toy theory, these are going to play the same, these epistemic states are going to play the same sort of roles as the corresponding quantum states that you would normally write with these symbols. Now, as well as knowing the answer to one question, the knowledge balance principle said at most, right? So we could also know the answer to 0 questions. If you know the answer to 0 questions, you have a state of non-maximal knowledge, which in this case is just a uniform distribution over all 4. And this is going to be the analog of the maximally mixed state in quantum mechanics. Okay, now let's talk about measurements. So how are we going to deal with measurements in this theory? Well, we're going to make 2 demands on the measurements. First of all, we want our measurements to be repeatable. They should yield the same result if we perform the same measurement twice in a row. And we do not want to violate the knowledge balance principle. So anything we do to our system should leave the system in a valid epistemic state. So one of these 6 states that we just talked about. So this immediately implies that there cannot be a measurement that reveals the exact ontic state. Why? Well, suppose the measurement revealed that we were in this ontic state here, bottom right-hand corner. Then in order to be repeatable, the system would have to stay in that state. And if it stays in that state, then we now know the exact ontic state, which violates the knowledge balance principle. Now, however, we can have measurements that reveal coarse-grained information about the ontic state, provided they also disturb the ontic state. So we're really deriving in this theory from the fact that we want the knowledge balance principle to hold, the fact that measurements must disturb the system. So here's an example of a valid measurement. So I'll call this an X measurement. And let's suppose it has 2 outcomes, +1 and -1. And if I'm in either of the left 2 ontic states, it gives me the measurement outcome +1. If I'm in one of the right 2 ontic states, it gives the answer -1. Now suppose we apply this measurement to the 0 state. Sorry, my light has turned off. This happens in my office from time to time. 1 second. Right. So suppose we apply it to this state here, where we have, it's one of the 2 states on the bottom, but we don't know which. If we get the +1 outcome, then we know that before the measurement, the ontic state was definitely 0, 0. This is the only one that had a non-zero probability and gives the answer plus. So if we do that measurement, then we would know that it must have been 0, 0 before the measurement. So in order to preserve the knowledge balance principle and maintain repeatability, there must be some randomization process which swaps these 2 ontic states. So with probability 1/2, nothing happens, and with probability 1/2, these 2 states get swapped. And that would preserve repeatability because I'm only swapping between states that have the same outcome of that measurement. It preserves repeatability, and it preserves the knowledge balance principle because now I'm in a valid epistemic state after the measurement. So the updated epistemic state will be plus. Lydia is telling me there's a question from YouTube, which is how do you calculate or identify the number of questions that define the given states? Okay, so in this way of doing things, right, you start by saying you have a system which has n ontic states, and then you know that the number of questions is how many times do I have to divide that number in half before I get to 1. Okay, so that's basically going to be the logarithm to base 2 of the number of ontic states. Now this is only going to work, of course, it's only going to give you a nice integer answer if the number of states that you're dealing with was a power of 2 to begin with. Okay, so this theory that we're talking about at the moment only really works for sets of ontic states that are powers of 2. Later on, we'll see how to construct the theories more generally for other sizes of state space. Okay, so I hope that answered that question that came in. Lydia, it would be helpful if you could give me an indication of how long I have left. Okay, right, so we can look at the measurements now. So these are going to be the valid measurements on the toy bit, and they're eigenstates, if you like. I'm just that in inverted commas because they're going to play the same role as the eigenstates in quantum mechanics, but they're actually just probability distributions that give a definite outcome to these measurements. So we have the Z measurement, which basically tells you whether you're at the front or the back. The X measurement tells you whether you're in the left or the right. You also have this Y measurement that tells you, are you on this diagonal or that diagonal? Okay, and basically they're associated to these epistemic states. You know, this is the one that gives the +1 outcome. This is the one that gives the -1 outcome. Okay, so those would be the 3 valid measurements. Okay, now let's talk about dynamics. So reversible dynamics, this is the analog of the Schrödinger equation or unitary dynamics. This is just going to be a permutation of the underlying ontic states. If you permute the underlying ontic states, then you can compute what that does to the epistemic states. Okay, so if we take an example, let's look at this permutation. This permutation just says, okay, if you're in this state, you go to that one. If you're in this state, you go to that one. If you're in this state, you go to that one, etc. Right, so you can say, okay, well, if I've got this valid epistemic state here, well, this ontic state would go here, and this ontic state would go there. So I would end up in the plus state with a 50-50 probability of being in either of these 2 ontic states. So you can just do the same thing, and you can see what this does to all of the epistemic states that are valid. And you can see that this acts a bit like the Hadamard gate in quantum computing. It's not exactly the same, but it's similar. Okay, so a question from Discord. Can the set of possible epistemic states depend on the choice of questions set? Okay, so the point is that, okay, in order to find the epistemic states, what you have to do, the valid epistemic states, what you have to do is choose a question set and choose a particular question set, and then choose half of those questions to be the ones you know the answer to. Now, in order to get all of the possible epistemic states in the theory, in general, what you have to do is you have to consider all possible minimal question sets. And for every one of those, you look at what happens when you know the answer to any half of the questions, right? And you'll get some repeats when you do that, but in principle, you have to go through all of those. But again, later on, I'll show you a better way of doing things, which allows you to construct these things without having to go through all of that. Okay, so next I'm going to talk about composite systems. So now we suppose that we have 2 toy bits. Each toy bit is going to have its own ontic state. Okay, so bit A, Alice's bit, if we say, and Bob's toy bit, they each have 4 possible ontic states. Okay, so to specify an ontic state of the composite system, I have to specify a state for Alice's toy bit and a state for Bob's toy bit. So there'll be 16 possible ontic states, 4 times 4. And if we have 16 ontic states, the logarithm to the base 2 of 16 is 4. So it's going to take 4 yes/no binary questions to specify the exact ontic state. So the knowledge balance principle is going to tell us that for this composite system, we can know the answer to at most 2 of those questions. But there's a subtlety. You not only have to apply the knowledge balance principle to the global system, but also to the individual systems. Okay, so here's 2 toy bits, right? So these are the possible ontic states of Alice. These are the possible ontic states of Bob. This probability distribution here satisfies the global knowledge balance principle, right? Because let's see, what can you just ask 2 questions about Alice's bit. So you just say, is Alice's first bit 1? Is Alice's second bit 1? And then you know Alice's bit exactly, but that's 2 questions, right? So it satisfies the global knowledge balance principle, but it doesn't satisfy the local knowledge balance principle, right? Knowledge balance principle has to apply if we look at Alice's system on its own or Bob's system on its own. So Bob's system's okay because we don't know anything about which of these 4 states we're in, but Alice's system is not okay because you know the exact ontic state of Alice's system. Okay, so you have to apply the knowledge balance principle to the global system, but also to the local systems. And that means that it's in principle even harder to write down all of the epistemic states, although you can do it. But here's just some examples of epistemic states, right, that are valid in the theory. Now, some of them are just products of independent distributions of the 2 toy bits. So you choose a valid epistemic state for toy bit 1, you choose a valid epistemic state for toy bit 2, and you just have them in those states with no correlations. And so here's some examples of those. But we also have states which are correlated, where the questions that you know the answer to are not about each system on its own, but about how the 2 systems are correlated with each other. Okay, so in this state, we know something about how the 2 bits are correlated in each of these 3 states. In fact, we know something about how the 2 toy bits are correlated, but we actually know nothing about the ontic state of each individual toy bit. Okay, another question from YouTube. For an elementary system with 4 ontic states, is the following a valid epistemic state? P equals a third, 0. The answer to that is no, because you have to start with a minimal question set, and you will always know a minimal question set always divides the set of ontic states in half. Each question divides it in half. Okay, so you'll only ever get the 6 ontic states, so the 6 epistemic states that I gave earlier, where 2 ontic states have 50% probability and the other 2 have 0. Okay, so continuing on. Okay, so these are going to be the analogs of the entangled states in the theory. Okay, so now let's look at dynamics on the composite system. Now we need to preserve the knowledge balance principle for subsystems, not just for the global system. So now it's no longer going to be the case that all permutations represent a valid dynamics for the composite system. For example, consider this permutation which switches these 2, it switches these 2, and it switches these 2. Okay, this I've just designed to make it so that if we take this valid epistemic state here, what will happen is this thing will stay where it is. This one will get mapped down to the bottom. This one will get mapped down to the bottom, and this one will get mapped down to the bottom. So it takes this valid epistemic state to one that we've already decided isn't valid. So in principle, you're not going to get all permutations. You have to look at the permutation and check that it doesn't map any valid epistemic state into something invalid that doesn't satisfy the knowledge balance principle. Again, when we look at the sort of Hamiltonian version of this, we'll see that there's an easier way to determine which permutations we have to use. Okay, so probably in the remainder of the time, what I'm going to do is, this is basically the setup of the theory that we've got. What I want to do is explain some of the quantum phenomena that this theory can capture. Okay, there are many, many more that I won't have time to discuss. In fact, the number of examples that were in the original toy theory paper is quite vast. So one should still take a look at that at some point. Okay, but here's one simple thing. Let's take the indistinguishability of pure quantum states, right? So you well know that if I prepare a state, the state 0, qubits in the state 0, or in the state plus, which is a superposition of 0 and 1, equal superposition of 0 and 1. So if somebody prepares the system in one of those two states with 50-50 probability and doesn't tell you which, there's nothing you can do to tell with certainty which state was prepared. Okay, so that we know from quantum mechanics. Now, the analogs of those two states, we can ask, well, why is it that in the toy theory that these two are not distinguishable? The reason is that because whichever of these two states is prepared, there is always going to be a probability of a half that the ontic state is the bottom left one here. When the ontic state is the bottom left one, there's absolutely nothing you could possibly do. There's no machine you could put this thing through that would give you any information about whether this or this was prepared, because you've ended up in exactly the same physical state, right? There's nothing you can do. So when it happens that that you're either here or here, then you can't do any better than randomly guess it. Okay, so the probability of making an error is going to be, well, with a probability of half, I'll be in this bottom left ontic state, regardless of which epistemic state was prepared. And then I can't do any better than 50-50 guessing. So the probability of error would be a quarter, at least a quarter. Note that in quantum theory, the optimal probability of error for these two states is actually lower than that. It's about 1.146 if you know about optimal state discrimination protocols. So the measurement that you have to do is not one of these XYZ basis measurements, it's something else, and it doesn't have an analog in the toy theory. And actually, there is an interesting connection between optimal state discrimination and contextuality. So we know that you can't do it as well as that, because a theory which does state discrimination as well as you can do in quantum mechanics has to be contextual, it turns out. So David might tell you something about that in his lectures. Okay, let's look at another phenomenon, the no cloning theorem. So here I flattened out the state space of a single toy bit. So let's consider a toy bit which is either prepared in the epistemic state, the 0 epistemic state, or the plus epistemic state. Okay, and now what we want to do is say, well, could there be a machine which, when I input this, outputs 2 copies of the 0 state? So both Alice's and Bob's bits will be, toy bits will be in this 0 state, so you'll end up in one of these 4 ontic states, or both in the plus state. Okay, so we want to say, can there possibly be a machine which would make this transformation? And the answer is no. And the reason is that, again, this ontic state, the system is going to be in this ontic state with probability a half, regardless of whether 0 or plus is prepared. However, we look at the output states, then the only overlap is this ontic state here. So the output states are in the same ontic state with probability a quarter. Okay, so the cloning device, whatever it is, only has access to the ontic state, right? It doesn't see what probability distribution is prepared. It sees which of these squares the system is in. So it can't do something different if the system is in this ontic state. It can't do something different depending on whether 0 or plus was prepared. So the output has to have at least an overlap of at least a half. They have to share, the ontic states. They have to have common ontic states to both of them, which have probability at least a half. But these don't, so you can't clone. Okay, and again, what we're seeing here is the fact that these states here, the fact that we're dealing with a psi-epistemic theory, the fact that we're dealing with a theory in which the analog of the quantum state is a probability distribution, and those probability distributions can overlap, is what is explaining the phenomenon here. So if you imagine that you were in a psiontic situation where the quantum state is a state of reality, then it's puzzling that you have two distinct states of reality, two really distinct things out there. They're physically distinct, and yet you can't tell the difference between them. That seems more puzzling. So this is supposed to illustrate some of the advantages of this psi-epistemic point of view. I'm not going to say too much about this. Let's consider the EPR experiment. The EPR experiment works just as EPR expected it to, right? Basically, there's a local hidden variable theory. So if you start in one of these correlated states, then we can imagine that Alice makes the Z measurement, or we can also imagine that she makes the X measurement. But let's just look at the Z measurement. If she makes the Z measurement, she's going to find out whether the system is basically on this side or that side. Okay, let's suppose she finds it's on this side. Then there will be a random disturbance. This is a local random disturbance, which is just swapping Alice's ontic states. And so this will get mapped into this, and the system will end up in the 0, 0 state. So then when Bob subsequently measures in the Z, he will find the outcome +1 as well. And the same thing would happen if she measured in the X basis. It's just that she would be learning, is it this, is it these two columns versus these two columns instead of the two next to each other. Okay. Right. Now how much time do I have left? I will hear the answer to that in a minute. So I just want to say, I'm not going to go through all of these, but here are some of the other, okay, 5 to 10 minutes. Okay, let me take 5 minutes. Here are some other phenomena that are reproduced by the toy theory. There's just a whole list of them. Many, many more. There's been a whole bunch of papers on this now. There are some things that don't arise in these theories. Bell inequality violations, obviously, it's a local theory. Contextuality. Quantum computational speedup is a little bit more controversial here because there are some things to say about oracle models here. But if it exists, assuming it exists, which most of us think we do, exponential quantum computational speedup, like we expect is the case for Shor's algorithm, doesn't seem to arise in these theories. And again, it's some details of the things on the left here, right? So I might say that teleportation exists in this theory, right? There's something like teleportation. But if you imagine that you are, if you imagine that you have a situation with some noise, for instance, and you want to ask, can I teleport? What's the optimal probability of doing a correct teleportation in that scenario? The exact numerical details of it won't necessarily be the same as in quantum mechanics. So this is, again, at the beginning, why I emphasized it's important to distinguish, what aspects of the phenomenon do you want reproduce. So, you know, the example I gave with the state discrimination already showed that, right? So you have the basic idea of state discrimination, but the toy theory doesn't get exactly the same optimal probability as you get in quantum mechanics. Okay. So I'm not going to spend a lot of time. I'm just going to do the intro to this bit. And next time, I'm going to spend most of the time talking about this and how to construct these theories in more generality. But you see, interference is often thought of as the sort of key knockdown argument in favor of the reality of the quantum state. So we're trying to show that that isn't the case. So this is a paper that we recently put out with myself and these three collaborators, which aim to show that, you know, to show in detail how interference can work in this kind of theory. Now, you know, there is an account of interference already in Spekken's original 2007 paper, but it's just not very explicitly worked out exactly how, for instance, an interferometer would work. So that's what we're trying to do here. But I just want to point out that, you know, how pervasive this argument is. That so I want to, you know, actually look at three things that we were trying to sort of argue against in this particular paper. So first of all, quantum interference implies the reality of the wave function. Right? This is by far the most common argument given in favor of the reality of the quantum state. You may know about things like the PBR, Pussy-Barrett-Rudolph theorem, etc. But you know, if you go around talking to people and you ask them, why do you believe in the reality of the quantum state? If they do, the answer is almost always something like interference. So this is what Tim Maudlin says in his textbook. It says, interference is a real observable physical effect and it requires a real physical cause. Such a cause must behave in a way that corresponds to how the wave function behaves. So that's saying it's a strong argument, you know, for having a real wave function. Of course, Feynman is famous for saying that, you know, interference is somehow genuinely non-classical, right? So he says, you know, this is a very famous quote, but he says, you know, in reality, it's the only mystery, and it's absolutely impossible to explain in any classical way. We argue the opposite. This theory that we're talking about is a perfectly classical theory. There's also an argument that's often actually this argument often appears in the philosophical literature, less so in physics. But so here's David Albert giving this argument. The idea is that the superposition of two states is somehow a new category of existence. You know, so if I have a superposition of being on the left and the right, that's somehow a completely different category than being on the left or being on the right, or just being uncertain about whether I'm on the left or the right. So he's talking here about an interference experiment, electrons in a sort of Mach-Zehnder interferometer type of setup. He says, what can such electrons be doing? It seems they must be doing something which has never been dreamt of before. If our experiments are valid, and if our arguments are right, electrons seem to have modes of being or modes of moving available to them, which are quite unlike what we know how to think about. The name of that new mode, which is just a name for something we don't understand, is superposition. So this is the argument that superposition is somehow a new category of being. Okay, so I think I'm going to stop there. I just want to say that, so what I'm going to do next time is show how in a Spekens-like toy theory, we can reproduce the phenomena of interference that I usually regard as problematic. And then after I've done that, I will go on to talk about how you construct these toy theories in more generality, in more detail. So that's what I'll do tomorrow. Thanks for your attention today. I don't know if there's time for taking questions, but if there is, I'm happy to stick around.